Hey everyone. So this is problem number 4 from the acceleration packet on the summer assignment. So I'm sorry with the numbering, it doesn't show that it's number 4. When I pasted it here, it just reformatted it and I can't fix it. So we're just gonna live with this. But we're driving down the highway late one night at 20 meters per second when a deer steps onto the road 35 meters in front of you. Your reaction time before stepping on the brakes is 0.5 seconds and the maximum deceleration of your car is 10 meters per second squared. So part A, which is labeled number 1 here, how much distance is between you and the deer when you come to a stop? And part B is what is the maximum speed you could have and still not hit the deer? Right. So we see here we basically have a kinematics problem going on, right? We're given velocity, time, acceleration. Those are all things that are part of kinematics, and our acceleration is a constant value, so we're allowed to use the kinematic equation. So I'm just going to write here on the top just to remind ourselves what the kinematic equations are. So let me zoom in. No, that's not how I zoom. Okay, sorry, I'm still figuring out this this computer. Nope, that didn't do it either. Okay, I guess I can't zoom while I'm recording. Okay, well, I'll just try to write small. All right, so kinematic equations. Let me find a formula sheet. I do have them memorized, but just to write them in the order that are on their formula sheet. So the top 3 formulas on your formula sheet. So we have that our final velocity is our initial velocity plus acceleration multiplied by time. We have the position formula. So our final position is our initial position plus initial velocity times time plus 1/2 acceleration multiplied by time squared. And finally, the no time equation. That should be a subscript of x there. All right, so we have our 3 kinematic equations here. So what we want to do first is kind of draw what's going on. And I'm going to draw this kind of in 3 parts, so to speak. So we have initially, here's our car, and our car is driving, and it's driving with an initial speed of 20 meters per second. For this problem, so it's a one-dimensional problem, right, where we're either dealing with left or right motion, not up or down. So I'm going to call to the right our positive x direction, right? So my initial velocity, our car is moving to the right here, so at least I'm saying it's moving to the right, so it's going to be a positive 20 meters per second. So it's going to be moving at that speed until I reach the time of 0.5 seconds, all right? So it's basically throughout this motion, between these 2 moments in time, we are not accelerating. Our acceleration here is 0. Until we reach this moment in time where we're still moving at 20 meters per second, but this is at the time of 0.5 seconds. Now we start to brake. Now we start having an acceleration, a constant acceleration of negative 10 meters per second squared. Negative because we are going from a positive so we're moving to the right, but we're slowing down, which means our acceleration is the opposite direction of our velocity. So our acceleration is to the left, which is a negative value. And eventually we're going to come to a stop. We'll put that here. This is our stopping location. So that's at some mystery location, but we know when we stop that our velocity is going to be 0, right? So when we come to a rest, we don't have any speed. Okay, so let's just kind of keep these in mind when we solve the problem. So first, how much distance between you and the deer when you come to a stop? All right. Well, there's a couple different ways we can solve this. So we basically have 2 parts here. We have the first part where we have this 0.5 seconds of reaction time. So let's find out how far we travel from when we first notice the deer to when we then start hitting the brakes. So since we want to find position, that leaves us with the last 2 kinematic equations, either the one that involves time, the position equation, or the no time equation. Well, since we know it takes 0.5 seconds, so half a second for us to start hitting the brakes, we can then just use the position equation. Okay, so for part A, we have our final position is our initial position plus initial velocity times time plus 1/2 our acceleration multiplied by time squared. In this first part, we're dealing with our reaction time. We haven't hit the brakes yet, so we're not accelerating. Our acceleration is 0. We're just coasting at 20 meters per second. So I plug in 0 for our acceleration. I'm going to call our initial position, this spot here, this location being 0. So we start at 0, and I want to see how far we go from that 0. So we're solving for a variable x here. We're saying we start at 0. So essentially now our equation just reduces to our final position is going to be, well, our initial velocity multiplied by time. So we take our positive 20 meters per second multiplied by our 1/2 second, and we get a value of 10 meters. All right, so now we have found that, oh God, I don't want to make this messy. This location here is at 10 meters. But that's not our final answer, right? We know we traveled 10 meters, but we want to see how much distance between you and the deer when you come to a stop, right? So now we want to find our final, this guy right, oh, I didn't draw anything. This guy right here, our final location. And we had to split up the problem because to use the kinematic equations, we need acceleration to be constant. So we had to break this problem up into 2 parts. One where we're not accelerating, and then now the part where we are accelerating. So now we need to basically solve the second part of this equation, where we don't have time, right? So that kind of leaves us with the no time equation to solve this. So that might be a good idea. So this next part, I'm basically looking at the second half of the situation. So now we are hitting the brakes, and now we want to see how far we go. We can take 2 approaches in terms of location. We can call our initial location 0 if we wanted to, and kind of rethink our problem from there, or we can be consistent with what we've labeled and call our initial location being 10 meters, and still have our 0 be when we first see the deer. I'm going to solve it that way. So our problem here states that our final velocity squared is our initial velocity squared plus 2 times our acceleration multiplied by our displacement. Right? Well, now we know our final velocity is going to be 0, right? We want to see how far we go. So we're solving for that x value now when we come to a stop. Right? So at our final location, our speed is going to be 0. So that's why that value there is 0. Our initial velocity, we know that value, that's going to be 20 meters per second. And we have an acceleration, that's negative 10 meters per second squared, and our initial position we're going to call 10 meters. So kind of continuing on here, we have 0 is equal to our initial velocity squared plus 2 times our acceleration multiplied by our displacement. All right, we're solving for that x value, so I'm going to first subtract initial velocity from both sides. All right, and now I'm going to divide by 2a. Which leads us then to isolate x, adding x naught to both sides. So our final position is going to be negative initial velocity squared divided by 2 times our acceleration plus our initial position. Okay. So now it's just a matter of plugging in numbers. All right, so God, can I squeeze this in here? Oh, yay, I can move things a little bit. Okay, that's beautiful. So let's just plug things in here. So we have negative our initial velocity, which is 20 meters per second. Square that quantity, so careful. That negative is on the outside of that square. Very important, as we'll see in just a second. 2 multiplied by our acceleration, which is a negative 10 meters per second squared, plus our initial position, which is 10 meters. Okay. So now we plug this in. So we look here and we see our negative signs cancel out, which makes sense because we know our position is going to be in our positive direction. If we got a negative position, that means when we hit the brake, we start going backwards, which is not the case here. And doesn't make sense if we're moving at 20 meters per second initially. So we take 20 squared divided by 20 gives plus 10, gives us a value of 30 meters. So 30 meters from our initial position is where we stop. All right, so what does that mean? How far are we from the the deer, when we come to a stop, says the deer is 35 meters ahead of us, and we reached 30 meters. That means the deer is 5 meters away. Right? Moving on to part B, what is the maximum speed you can have and still not hit the deer? All right, sorry for instantaneously scrolling. I just had to pause for a second. Okay, so we want to find, what were we trying to find? Sorry. What is the maximum speed you can have and still not hit the deer? All right, so now we basically want to see, if we're not hitting the deer, basically we want to travel that 30 or just under that 35 meters. So we're going to assume now that our final position is 35 meters, and we're going to solve the problem where our initial position is still 10 meters. I'm going to make that assumption. You could solve this, sorry, that was supposed to be an X. You can solve this where your final position is 25 meters and have your initial be 0. That's completely valid here. But I'm just going to use this just to be consistent. Our final speed is still going to be 0. And we want to know what our initial speed is going to be, right? And we still know our acceleration is still going to be that negative 10 meters per second squared, right? Again, we don't know time. We could solve for time and do it that way. I'm just going to use the no time equation again. Right, but this time we are solving for our initial velocity, right? So basically, we just take our final velocity. Well, let's plug in zeros, actually. Let me erase that. Oh, nice. So that value is 0 there, and nothing else, at least in my conditions, are 0. So we have 0 is equal to our initial velocity squared plus 2 times our acceleration multiplied by our displacement. So kind of rearranging here. Luckily, we don't have to do much. We bring over our initial velocity to the other side. So then now I just needed to multiply both sides by -1 to cancel out that negative sign. So that's just the same thing as switching those. And now I just take a square root. Square root of 2 times our acceleration, x naught minus x. Right? It's important that switch because our acceleration is negative, and we don't want our answer to have a negative underneath the square root, because then our answer would be imaginary, which is not physical in our class. So acceleration is negative 10 meters per second squared, and then we have our initial location of 10 minus 10 meters minus our final location of 35 meters. All right, so doing this computation, we have the square root of 2 times negative 10 times the quantity of 10 minus 35 gives us a value of about 22.4 meters per second. All right, so that's this. We're going to have to be under that speed in order for us to break in time. All right, so hope that was helpful. Now, how do I stop this recording?